Alrighty, let's talk about vectors then. And so our vectors, we said our vector quantities have magnitude and direction. And so far we've mentioned displacement as a vector quantity. Now the good thing about vectors is that we can draw them to make them quite easy to see what's going on. When we draw a vector, it's a line with an arrowhead. And it's probably not surprising that the arrowhead points in the direction of the vector. So this can be a vector. You might see vectors represented with a little arrow on the top of them like that. Or it could be written as an underscore, like that. And in some textbooks, it's written in bold. But that's a way of indicating that whatever it's talking about is a vector quantity. Now, vectors are, as I said, very useful, and we can do a few things with them. One of them being add them together. So that if we've got a few different stages of motion, for example, we can add those separate stages of motion together to find out what happened overall. So if we're going to do some vector addition, we have a rule, and that is that the tail of the second vector needs to be positioned at the head of the first vector. So we position our head to tail. So if we have a look at an example here in our booklets where we had our swimmer where she moved the 10 metres from the blocks, from behind the blocks up to the pool, and then if she swam 50 metres after that, I can represent that as vectors by putting the tail of the second vector on the head of the first, and that tells me that for total displacement, is 60 metres. Okay, all we've done is we've positioned those vectors according to our rule, and we've just drawn a third vector to represent what that looks like overall. Now just say she did something different, and she goes 10 metres up to the blocks, and she swims the 50 metres, and then she comes back 25 metres. Then we can still represent all of that with vectors, because this one, even though it's pointing in the opposite direction, is obeying our rule where we have to put the tail of our next vector on the head of the previous one. And so our total displacement in this case is equal to 10 plus 25 is 35 metres. And again, because we're only working in one direction, one dimension, I'm not not writing any directions because we're only talking about along the x-axis. Right? Things will change in a moment. Is that seeming okay, that that's a reasonable thing, that we're doing it without adding of our vectors? Now, we'll get on to set one in a moment, but what I want to do is let's sort of make things a little bit more realistic, if you like, and because we don't all just walk in straight lines like that, as in just along the x-axis. What you need to be, yep.
Sorry, I just had a quick question.
Sure.
With your diagram, you did the 10 meters and then like the 50 meters. But does it start at 0?
In that vector one, I was just adding the vectors.
So your 0 was at the end?
My 0 was at the end of the vector.
Whereas in this one, if like she'd gone to the 50 and the 10 was negative 10, would it just be 50? Because it was 50 from 0.
Yeah, so if we're positioning it on the number line, then that's different to just looking at adding vectors.
Okay.
That's giving her position, whereas what I was trying to, it was probably not, I was matching it up with the vectors in here, in the booklet, but it probably would have been better to use a different example so that we weren't trying to overlay the results with the previous questions.
Yep.
Let's have a think about motion in two directions. And so we've got a worked example on the bottom of page 8. In this example, Jessica is a bushwalker and she hikes 5 kilometres north. And you will need to know your compass for this unit as well. Then 8 kilometres east. Okay, this is her starting point. And that's what she did. And this is her finishing spot here. Okay, that's where she stopped walking. So her distance that she travelled is fairly straightforward. This is just the pathway here, all the way along there. Is going to be 5 kilometres plus 8 kilometres is 13 kilometres. But if we want to work out her displacement, remember that our displacement is our location in respect to the origin. So this is the origin here, that's where we started, and that's her location right now where she finished. So my displacement is this. Notice that I haven't made a triangle where this vector joins back onto the end here. Okay, I'm not adding vectors here, I'm finding the answer. So I added these two head to tail, but this one is my resultant vector after I've added all my vectors together. And so it has to start at the origin and it has to end at her final location. Does that make sense? Or, okay. Now we need to do some calculations. Because this is a right angle triangle, trigonometry is going to help us out here. We know that this is the hypotenuse. And to find the value of, if we say it's x, x will then equal the square root of the other sides squared, which we get 9.4 kilometres. Now, that is the length of the vector. So remember, our vectors have magnitude and direction. So we've found out how long it is now, but we need to know direction. And we need to bring our direction back to our compass points. This is my angle theta in here, which is what, if I had to tell Jessica how to walk that same pathway, or tell somebody else how to find Jessica, to say Jessica's left her lunch behind and her brother Joe is going to jog along this vector here to give her lunch. Well, he knows at the moment that he's got to jog 9.4 kilometres, which is a pretty good thing for Joe to decide to do. But we have to give him a bearing so that he's going to do a little bit of orienteering in order to deliver this lunch. So here we use our trig again. This was just Pythagoras' theorem. But you might remember that tan theta is equal to the opposite over adjacent. This is our most common trig ratio that we use in Phys Sci. So we've been given these. I like to use the ones we're given rather than the one we've calculated because it's more accurate. So that's going to be 8 over 5. And you might also remember that to find theta then is equal to the inverse tan of 8 on 5, which gives me 58 degrees, which is still half a direction, isn't it? We now know the size of the angle, but we're going to need to relate that back to our compass points. What does that angle 58 degrees mean in terms of the compass? Yeah, so what is it?
Would it be 58 degrees?
Well, yeah, see, this angle is that from north. Okay, this is actually north up there, isn't it? So we could say it's north, 58 degrees what?
East.
East. Because we go from one of our compass points, north, south, east or west, normally north and south, and then we talk about the angle from there. So we've gone from north, from due north, 58 degrees towards the east. Now Joe is going to be able to safely jog that sandwich up to Jessica because he knows the angle. Okay, does that make sense-ish? Okay, there's another example that I think we're going to skip question 1 at the moment in set 1 because I'll bring some string on Thursday. But I'll get you to do questions 2 and 3 and have a go at the worked example 4 on page 9 and then see if you can work through the questions in set 2 as well.